Welcome back, ladies and gentlemen, to the YouTube channel, where today I would like to show you the simulation of a biochemical reaction using Scilab. First, I will make the function which is making the calculation for it. So biochemical reaction will be simulated, and now I will make the author node, my name at GitHub, and I will upload all materials. You will be able to download everything from there. The reaction itself will be that an enzymatic reaction. We have enzyme plus a substrate, which will be reversibly make an enzyme substrate complex, and then it will turn to make enzyme plus the product. So this is the biochemical reaction what we will describe now in the simulation. You will see that the enzyme is connecting together with the substrate, then it is associating to an enzyme substrate complex. Then it can also make dissociation and split to enzyme and substrate, but we expect primarily to make a product, and of course when the substrate is transformed to product, we receive the enzyme back. So we will make a calculation, and the input of the functions must be on first place the enzyme, and second place will be the substrate, the third what we need is the enzyme substrate complex. These are concentrations, so the amount of the given material. And what we need more, we need kinetic constants. I will make key on and key off names. Key on will be the production of the complex, and key off will be the dissociation of the complex back to enzyme and substrate. So there will be already 5 parameter, and the parameter number 6 will be the kinetic constant for production when from the complex we produce the product. So these are all the input variables we will use. So we have an input vector for our calculation, and the output vector will be all the changes. What can change? Of course, the enzyme concentration will change. So the enzyme change over the time. The second will be the substrate change over the time, and the third will be the enzyme substrate complex change, while the fourth will be the product change. So this function, what we are going to make, will have 6 inputs and 4 outputs. So I will make the function, and the return variable of the function will be the output. It will be a vector, and I have a reaction and with the data vector. This is the input for my function. The return variable I fill with zeros initially. Zeros. 4 zeros I will save into it, and then I have to calculate all equations one by one. These will be chemical concentrations what we can calculate. So first, the enzyme quantity change will be how it is changing. The enzyme quantity will decrease because we produce the enzyme substrate complex. So minus key on the complex production kinetics multiplied by the enzyme multiplied by the substrate, because these concentrations are driving the biochemical reaction, how they make the complex. And when the product is made, we can also get back some enzyme, and also together with the dissociation, so it is double direction. Also the dissociation and the production make enzyme based on the concentration of the enzyme substrate complex. So I can say plus, and two things, the dissociation, the key of, plus the production, key production, kinetic multiplied by the enzyme substrate concentration. So this is the equation what we exactly have to do. It means that the return variable, return array first element will be, now we have to turn this to data vector elements. The first will be the key on, it is element number 4, minus data vector element number 4, multiplied by data vector element number 1, and multiplied by data vector element number 2. So the first is ready. And then plus, we have two kinetic constants of and production, 5 and 6. So data vector 5 plus data vector 6 together, and this summary should be multiplied by the enzyme substrate complex, which is data vector number 3, element data vector number 3. I finish all lines with a semicolon because I don't want to see the result on the screen. Meanwhile, I don't want to see the logs. Okay, the next one will be how the substrate is changing. The substrate change will be, of course, the same way. The production of the enzyme substrate complex will decrease its quantity. So the key on kinetics, how we make the complex, multiplied by the enzyme and the substrate. The beginning is the same, and we have no substrate here in the production side, so only the dissociation will give us back substrate, if any. So plus key of multiplied by the enzyme substrate concentration. So return variable, value of array number 2 will be the second value. If I copy from the previous one, because I'm lazy, what can I do? I need, the beginning is the same, plus the key of only element number 5. So the 6 should be deleted, and now it's ready. Only number 5 multiplied by number 3. So key of multiplied by the enzyme substrate concentration. This way we have depending differential equations, and we solve all of them once now. What will happen with the next one, the enzyme substrate complex concentration? Of course, it will increase as the enzyme and substrate altogether form the complex. So plus key on multiplied by enzyme multiplied by the substrate. Okay, this is forming it. And minus, we can see that the enzyme substrate complex is dissociated in one direction back to enzyme plus substrate, the original state, and also in the other direction forming the product. So minus, again, key of plus key production, the kinetics, multiplied by the concentration of the enzyme substrate. This is driving the reaction. So the return value number 3 in the array will be, if you can see, this is very similar to the first one, only the kinetic constants are -1 here. So basically I can copy the first equation, and I have to adjust only the signs. At the beginning we have plus, so the minus I can remove, and then between them here I have the minus. When the key of and the key production, kinetic constants all together, and yes, I'm ready. And then the production, how it is coming, it will be the kinetic constant of the production multiplied by the enzyme substrate concentration. This is the only way how they depend, and this is only one directional reaction, so it doesn't form back, doesn't make back the enzyme substrate complex. So the return value number 4 will be the data vector production number 6 multiplied by the enzyme substrate complex concentration, data vector number 3. This is it. And here I would like to highlight that this is plus. Okay, so now I am ready with this reaction. Okay, and let's see how it looks like. First, I will save, and I will make it reaction name. Okay, and now I can run. Here you can see that there is basically no error message. So this reaction function I can use with 6 input parameters: enzyme, substrate, the complex forming kinetics, dissociation kinetics, and production making kinetics. So let's try how it works. The reaction function has the parameter of a list of numbers, one array. So the enzyme concentration, let it be 1 at the beginning, 1 at the substrate concentration. The enzyme substrate complex is 0 because initially we don't have at all. And the kinetics, the production of the complex should be, let's say, 0.5. The dissociation of the complex back to initial state 0.1, and the production 0.3. I would like to use these parameters later on in the simulation, and now we will check what is it. We can see that the enzyme and substrate concentration are decreasing and the enzyme substrate complex concentration increasing. The production is nothing at this stage. So it seems that the reaction function is working. There is no problem, no mistake in it. So the source code what we made is working. There is no error. Okay, we are very happy with that. I will move this to the side because I will use this function in the simulation using the application of Xcos. This is a graphical simulation interface. We have one workplace here and one palette browser. I need the inputs here and the function code to be able to check that what I am doing is correct. I have the correct connections. So what can I do? Maybe later I will increase the size of this area. I need some inputs. Some will be the concentrations I will use, but I have 3 constant values. The kinetic values for the on, off, and production kinetics. So from the sources, I will use the constants. No, it doesn't want to go, so I double click and then I have 1. Okay, this will be the on set of my complex. So this will be the first one. Then I will have the second one here. It will be the offset, the dissociation of the complex, the same values what I used in the trial of the function. And now it will be the production kinetics. Okay. And here I will say that all kinetic constants are in 1 per minute. So kinetics in the unit of 1 per minute. So I imagine this situation and all the simulation in minutes. It will have importance later when I adjust the time frame of the simulation. So the title will be Biochemical Reaction, and the reaction I am simulating is enzyme plus substrate is forming first reversible way an enzyme substrate complex, and then only one directional enzyme plus the product. Okay, so this I will make it larger, and okay, it will be here. So this will remind me what is my simulation. And the core of the simulation will be the function, which has 6 inputs and 4 outputs. 3 constant inputs are here already, but I will have 3 others. To collect them all together as an input vector to my function, I need signal routing. In signal routing, I will use the multiplexer. I put the multiplexer here, and first I bring this to the place, and then make it a bit larger, double click and adjust the 2 input to 6. So I will need 6 inputs. Okay. Oh, it's not good. Okay, so I have it. For some reason it did disappear. I will make it thicker a little bit, then it is easier to move. Okay, you can see here I can connect it already to the multiplexer. I prefer straight lines because if you follow this very simple editing principle, later our work is much more easy to figure out what is connecting to what. So I just adjust the lines. It will be more easy to follow later on what happens. So I collect all the inputs for one function, what I made already. It will be a Scilab function block. This is the core of the simulation. This will calculate the changes. And if I double click on it, I can adjust the block parameters. The input port size will be 6 because I have 6 values arriving on input port number 1, and I calculate 4 values, so I will have 4 leaving parameters. And the heart is not a sine function, it will be my own function what I used already, the reaction. The name of the function is reaction, what I created here and tested already in the console. So I click OK. No other setup adjustment is necessary. I leave everything default. Okay, to remind myself what I need here, I can list all things. Enzyme is the first. The second is the substrate, just to remind myself how I have to connect them. Enzyme substrate is the third. Then comes the kinetics, key on, kinetics, key off, and kinetics production. Okay, so these are basically all the parameters, and now they are listed here next to the multiplexer to remind me how I have to connect the parameters. Of course, I have an output as well. So I make a copy of this because I'm lazy. I put it here. So what I will calculate one by one. First will be the calculation of the enzyme change, the substrate change, enzyme substrate change, and the change of the product. Of course, these are amounts. Okay, so now it is ready. So this function will give me an array, a list of numbers, and this list of numbers I have to decompose to be able to calculate. So again, with the signal routing, I will use the demultiplexer. Double click on it and bring to the place, make it a bit bigger like I did with the other, double click, and now it will have 4 outputs. The 4 outputs will be like what I put there, a little bit thinner, it's not bad. I connect it, and you can see here that the blue line will connect always the data, red will be for the clock, the timing signal. Okay, I just put it closer to the demultiplexer. What I have to do with it? Okay, because I have here the changes over the time, of course I have to summarize it to get an accumulated value. It means that I need an integral. So in the continuous time system, I have to integrate it. I have 2 integral opportunities. I will use the integral function. The other one is more like MATLAB compatible version. Okay, there will be a problem, it is too close, and I will make copy of it because I will need 4 altogether. Hey, I will have it. It seems I have problem with the drawing. No, okay. And one more. Okay, almost. This is the hardest part of the job, to play with the positioning of the elements, actually, to look it perfectly. I will enlarge the size so all the parts will be closer to the element what I want to connect, and now I will be lazy to connect it only with straight lines. This way, when it turns to green, I can connect all of them. And in the integrator, I have to enter the initial values. The initial parameters of the enzyme, I will make it 1 unit, and the substrate, I will make it 10. So only 10% will be the substrate, the enzyme at the beginning. The substrate will be 10 times higher, and no enzyme substrate and no product at the beginning. So I will double click here, initial values. Please always make comments to understand later what you are doing. So the enzyme will be 1 unit, the substrate will be 10 unit, the enzyme substrate is 0, and of course product is 0 because at the beginning we have no product. We do it all to have product later. So we design it to have production. So we have the 4 calculated values, and finally I would like to show it in one figure. It would be nice to see them all together. So I will make it bigger a little bit. Again, signal routing, I will collect all together into one figure. So with a multiplexer again, I have to collect all. With the multiplexer, double click, I need 4 inputs. Okay, and how they will be connected? Just this way, this way. I'm super lazy now. I'm not sure I will be able to adjust them better if I enlarge, but we'll see. A little bit better. Maybe it is possible to enlarge. Yes, I made it. Wow. It can happen that I can do the same with the demultiplexer, so it is possible to make it. Yeah, beautiful. They are straight lines now, and in the sinks I need a C-scope which will collect all information and will make a chart for me. So finally it will finish in a C-scope. Connect, and this will be the C-scope, the figure which will give me the result of the calculation. From the sources I will need a clock. This will drive all the simulation, and the clock signal is coming to the red connection of the figure. So here are the colors of the figure, the number, the size, it's okay. The minimum is 0 because I do not expect negative values in concentration or amount. The maximum should be 10 because the highest value is 10 for the substrate. The refresh period will be 5. The buffer size I will make at least 10 times higher. This is the recommendation generally. Luckily, the Xcos can expand it dynamically if I need higher buffer, but it's better to adjust a large buffer enough. The name of the scope will be, let's say, concentrations. So these are the results of the computation. Now, before I would be able to do any simulation, what are missing? I need the connection here, the enzyme, the substrate, and the enzyme substrate concentration. Actually, these are the so-called Canville-Thompson feedback theorem or feedback loop. The enzyme and substrate are calculated here. So these values will be connected back. Let's see how is it working. The enzyme I should connect to the first one. Okay, this is connected now. What about the substrate? The substrate I will get farther a little bit, and then it should come to the third one. Okay, and the enzyme substrate will be the third. But I connect all together. Oh, it doesn't look very beautiful. Now, because my line is here, I think I will move it over it. I don't like very much when lines are crossing each other, but if you move your mouse over it, you can see how they are connected. Maybe this text I can make it smaller a little bit, and then I will have enough space there. So this is the biochemical reaction. It is ready. Before doing anything, I save it for sure. So biochemical reaction. That's it. To be able to run the simulation, what I prepared, it will run for 5 minutes. I have to set up the adjustment here. You can see the final integration time will be 5 minutes. The real-time scaling, no need to change. Everything will be understood in minutes. The integrator tolerance, the amount of information here in unit, concentration in the range of 0 to 10. So I will make 0.01 tolerance. This is my accuracy, what I expect. I change the relative tolerance to the same value. The tolerance on time. Actually now the simulation will finish in 5 minutes. So if I am calculating everything in second basis, I think it will be far enough. So 1 second is how many minutes? 1 pro 60, it is 0.01667. So tolerance on time will be 0.01667. This will be the 1 second, so I calculate everything in second accuracy. The maximum integration time interval will be the 5 minutes. The time frame of the total reaction, the solver can be the default, and everything now is set up. Okay, I save it, and now I can run the simulation, how it looks like. I have the figure. Oh, this yellow is for the production. It is not so beautiful. Maybe I will change the color of that one, and maybe 6. I will change the color for the fourth element, and now if I run the simulation, you can see, okay, it seems that the 5 minutes is not so enough, not large enough for this reaction. What we can see here is the so-called steady state part of the reaction, because the enzyme substrate concentration is almost constant, the production is continuously increasing, the substrate concentration is continuously decreasing. What can I change? Of course, the concentration figure will change. The refresh period, I will make it to 50. I don't want to see only the last 5 minutes. I want to see the whole reaction because it is a scope. So 50 minutes, almost 1 hour. I will change the simulation time, simulation setup. I will change to 50 and also 50 here. Okay. Now I save and run again. It is much better, much more beautiful. So this is a typical curve how the simulation is working. Here you can see basically the steady state part when the concentration of the enzyme with the red curve is almost constant. The substrate with the green is continuously decreasing, the product with purple is continuously increasing, and the enzyme concentration is low because it was forming the complex. And when we are running out of the substrate, then the enzyme substrate complex will drive only the chemical reaction, and we are going over to saturation. So this is a typical kinetic curve how a biochemical reaction is running. The first part is the enzyme, the first value which we show here, it is black. This is the enzyme, drop down the concentration and later only increase when the enzyme substrate complex is dissociated back to the original substrate. The enzyme substrate complex is appearing at the beginning, maintained and then decreasing by the end of the reaction. The substrate concentration is decreasing continuously with different speed. There is one part when the change is continuous, almost linear tendency can be seen. This is called the steady state part of the biochemical reaction, and also the production, you can see it is increasing and finally reaching the saturation when the reaction will finish. So this is what I planned to show you today, how this biochemical reaction is working. You can see we did build first function, a model first, and then we tried this model. We built up in the visual interface using Xcos, and we were able to run it here successfully. So thank you very much for your attention. I hope you enjoyed and you will try this in Scilab, and you can download it from GitHub. Thank you very much.